Okay, welcome to chemistry. Today we're going to be talking about the shell model of the atom. Right? So recently in my class we've been talking about how the nucleus is very dense and very small. And it's the space outside that nucleus that's huge and vacuous. Very, very empty, where those electrons reside. So the shell model of the atom, excuse me, basically talks about electrons within atoms have different energies, which we call shells or energy levels, that are at different distances from the atomic nucleus. So in other words, the further and further an electron gets outside of the nucleus, the more energy it has. And chemists designate the locations of electrons by these numbers called quantum numbers. And their values designated to electrons to indicate the probable location where they can be found. In other words, if you know the principal quantum number, the secondary quantum number, and so on of an electron, you can tell someone the probability where that could be found, where the electron could be found at any given time. So the quantum numbers. The principal quantum number n indicates the shell number where the electron resides. For example, if n equals 1, that electron in particular is in the first shell outside the nucleus. If the principal quantum number is 2, that electron is in the second shell. A value of 3 for the principal quantum number would tell you that that electron is in the third shell, and so on. And then within these shells, there's subshells. Think of a book with chapters within it, right? Items within items, documents within folders within other folders, right? So within these shells, we have this concept called a subshell. They exist within each principal quantum number, right? The shell number, and they're designated by these letters S, P, D, F, G, etc. Okay. Shell number 1, the first shell, has one subshell called the S subshell. Principal quantum number 2, shell number 2, has 2 subshells, S and P. The third shell has 3 subshells, S, P, D, and F, and so on and so forth. Now, orbitals are not orbits like you've learned them in the Bohr model. They're not these circular, two-dimensional orbit diagrams. But they're three-dimensional spaces where electrons reside. They're the region of space where an electron of a given energy level is most likely to be found. That's an orbital. Now, within the subshells, the S, P, D, F, etc., each subshell contains one or more orbital spaces, vacancies, where electrons can reside. Depending on the type of subshell, S, P, D, F, that it is. Okay. Each orbital can hold a maximum of 2 electrons. That doesn't matter if it's an S, P, D, or F. They can only hold 2 electrons, maximum. So the analogy here is if you're trying to send a hard copy in the mail of anything, let's say a catalog to someone, you need to know that person's name, street that they live on, their city, and their state. And you would know their location, where they reside. The same analogy holds true of an electron. If you wanted to find out where in that space outside the nucleus is it found, you would have to know the shell number. You would have to know within that shell, the subshell. Is it in an S, P, D, or F? Within the subshell, you would have to know which orbital within the S, P, D, F subshell it's in. And finally, you would have to know what's called the spin of the electron. Okay? Now, electrons that buddy up, that partner up in the same orbital must have opposite spins to set each other off for stability reasons. So the spin of an electron is either up or down within the same orbital. Another way you could look at this is a diagram. The first shell has an S subshell, there's only one of those, and it can hold 2 electrons. The second energy level has 1 S subshell and 3 P subshells. And each orbital can hold 2 electrons. So our first shell can hold 2 electrons, and our second shell can hold a total of 8 electrons. Okay. Our third shell, to continue this analogy, has 1 S subshell, has 3 3p subshells, and has 5 3d subshells, for a total of 2, 8, 18 electrons can fit in the third shell. In the fourth shell, we have the addition of an F subshell, and there's 7 4f subshells within the fourth shell, for a total of 32 electrons. Good save. Okay, so now you try. How many electrons occupy the following? How many electrons total are in the 1s subshell, in the 2p subshell, and in the third shell? Okay. At this moment, pause the video, and I'll go over the answers. Okay, so I'm in the first shell, and it's an S subshell. There's only 1 S subshell, and it can only hold 2 electrons total. Our second question here, we're in the second shell, but it's a p orbital. Remember, p's, there's 3 orbitals. So there's 3 2p orbitals, and each one can hold 2 electrons. So that's 2, 4, 6 electrons total. Now we venture to the third shell. Now the third shell, there's a lot going on here. There is 1 3s subshell. There's 3 3p subshells. And there's 5 3d subshells. 3d, 3d, 3d. Each one can hold 2 electrons for a total of 2, 4, 6, 8, 10, 12, 14, 16. Our answer is 18 electrons.